Hi, everyone. My name is Stefan, and I'm going to be talking today about some joint work with Marco Carmosino at IBM Research. And that is our paper, Student-Teacher Constructive Separations and Unprovability in Bounded Arithmetic. So what I'm going to be talking about today is notions of constructivity in complexity theory and some notions that constructivity ought to be defined as in complexity theory, and how these definitions might relate to provability in first-order logic. So first off, what is constructivity in general? Well, in mathematics, constructivity means algorithms. So let's just go through some examples. Solutions for linear programming or solving systems of linear equations. You have easy, efficient algorithms to not only decide that there are solutions, but to extract them. Similarly, for planarity of graphs, not only is it efficient to decide if a graph is planar, you are able to produce very nice planar drawings very efficiently. And you also have the spectral theorem and various theorems on decompositions of matrices. Not only do you know these decompositions exist, you can produce them efficiently. Some classical non-examples, perhaps even surprisingly, would be the pigeonhole principle. If I have a map from n pigeons to n-1 holes, I don't know which hole is going to have the collision. I just know some hole will have one. Similarly, with the handshaking lemma, you don't know what other vertex is going to have odd degree. You just know that there will be one. And even with factoring, you don't know what the factors of a number are. You just know that there is going to be some unique prime factorization. Okay, so this makes sense broadly in mathematics, but how about constructivity as a notion for lower bounds in complexity theory? What would that even mean? So we'll be following the definition of refuters. So suppose an algorithm A does not solve some hard decision problem P over a range of input lengths N, then a refuter against A, which will denote R of A, will take in as input in unary N, and it will output a string of length N, where A of X is incorrect. It decides incorrectly whether or not X is in some language. For the purpose of this talk, a refuter is always going to be in polynomial time, but that may or may not be the case. Okay, so it turns out that refuters are actually a very interesting concept, largely because they're both necessary and sufficient to get lower bounds in computational complexity. So this was really first demonstrated by Gutfreund, Chaltiel, and Tashma in 2007, where they showed that if P doesn't equal NP, then there are actually polynomial time list refuters witnessing that separation. So what that means is if I give you some polynomial time algorithm claiming to solve SAT, then efficiently I can output up to 3 inputs, of which at least one, that polynomial time algorithm is going to be incorrect. We also know by more recent work by Li Chen, Sejin, Rahul Santanam, and Ryan Williams, that for many known currently non-constructive separations, making them constructive implies breakthrough lower bounds. So let's see an example of a classic lower bound that is constructive, and that would be the deterministic time hierarchy theorem. So let's say we're separating deterministic time n to the c plus 1 versus d time n to the c. So let's remind everyone how the proof goes. The proof is very simple. I'm going to come up with this fairly uniform hard language, which on input x will decompose x into the coding of a Turing machine concatenated with some zero padding to make it up to length n. If you are unable to parse x as such, then you can just answer true or false. Then, step 2, you run m on x for n to the c steps, and the normal diagonalization, if it accepts, reject, otherwise accept. And it's easy to see that you can solve m hard in time O of n to the c plus 1 by simulating machines running in time n to the c. So this is constructive, right? What's the refuter if I give you a algorithm a Turing machine M running in time n to the c to decide M hard, well, the output is just going to be the code of M and then padded out to whatever input length you desire. Going back to the proof, that is exactly what will incur the diagonalization. So here we have our first constructive lower bound. In contrast, it'd be nice to see something that is, in fact, almost seemingly inherently non-constructive. Shannon counting. Shannon counting is, of course, the classic theorem where there exists some truly hard Boolean function f, which is not computable by any circuit smaller than the maximum possible complexity. So to remind you of the proof of that, it's just counting. There are 2 to the s of n log s of n circuits of size s of n. You can do that through a quick encoding argument. And there are 2 to the n Boolean functions on n bits. And if s of n is smaller than 2 to the n over n, then you have a disparity in these two measures. So by counting, there's going to have to be some Boolean function not encoded by a small circuit. So if you notice, that very much was not constructive. I don't know which truth table or Boolean function is going to be hard. So let's consider a refutation version of this problem, where as input, I give you a truth table, and the language itself is going to be all the truth tables that are hard. And let's say I give you a clearly false algorithm by Shannon counting that always says, yes, the truth table is hard. Or sorry, the reverse, saying it's always easy. I would like to refute that algorithm, finding a truth table that's hard. Is that possible to do efficiently? Is there a refuter for this language A of hard Boolean functions, which runs in polynomial time? So in particular, given n in unary, n is the length of a truth table, output a string x, which this always yes algorithm incorrectly decides on. And this is a major open question. In fact, it's intimately tied to what would be breakthrough lower bounds in circuit complexity. So we don't know the answer to this question. And you can generalize this even further. Could maybe all lower bounds be made constructive? So these kinds of questions were intimately studied by CJSW in 2021. And they show several things. First off, giving constructive proofs of some known non-constructive lower bounds implies new breakthrough lower bounds. Similar to the GST result, most conjectured separations can actually be made constructive. So not only P not equals NP, but also say BPP not equal to X. And finally, some separations have to be non-constructive. So let's hone in on that third point for now, and also just in general for the rest of the talk. So let me remind you all what time-bounded Kolmogorov complexity is. If you fix a universal Turing machine U and let X be some n-bit string, then its k to the t Kolmogorov complexity is going to be the minimum length of a program and advice pair alpha, where simulating M on input alpha for t of n steps outputs X. So an easy folklore theorem, also proved by counting, would be that for any reasonable time length t, there exists some string X with high Kolmogorov complexity. Kolmogorov complexity at least n minus 1. Okay. And it turns out that this proof must be non-constructive. So an observation by CJSW is that if I let t of n be quasi-polynomial, n to the log n, and let the language L be these strings of high k to the t complexity, then there will be no polynomial time refuter for the always no algorithm. And how does that go? Well, quite simply, if there were a polynomial time refuter, then that means I am computing this hard high KT string in polynomial time, when definitionally that is impossible. Okay, So this is a fantastic notion of constructivity, but there is a flaw inherent to just focusing on refuters, in that while a refuter itself is going to be a polynomial time algorithm, it might be that the proof of correctness for this algorithm is extremely sophisticated and quite difficult. We'll get into what that means quite shortly, but this shows that perhaps CJSW's notion of constructivity and refuters isn't quite enough. It might be that there is, in fact, a polynomial time algorithm that's a refuter, but it requires very difficult concepts in order to prove correct. So we would like to study this notion. Okay, so this is where first order logic and bounded arithmetic comes in. So what is bounded arithmetic? It's a subset of piano arithmetic, these logical theories, which formalize, in some sense, notions of efficient proofs. So what we want is a logical theory T and a complexity class C, where the following two properties hold. First off, every function in this complexity class C can be provably total in this theory. So T would prove for every x, there's a unique y where you have f of xy. So this is known as definability. And then point two is something called witnessing, where if T proves some formula to be true, where it's of the structure for all exists phi, then that means there's going to be some algorithm in C, this complexity class C, witnessing the existential quantifier. So if T proves for all x, there exists y, 5xy, then there's some f in C where T proves for all x, phi of x, f of x. So a bit of history on bounded arithmetic. It was really first introduced by Perrick in 1971. He introduced this theory I delta naught, which characterizes the complexity class, the linear time hierarchy. And the language is quite simple. You have plus times 1, 0, successor, less than or equal to equals. You have the basic axioms of arithmetic, like distributivity. And you also have a bounded version of induction, where you have normal induction, where if you prove the base case and an inductive hypothesis, you get for all x, a of x. But now these formulas A must be delta 0. This means that every quantifier must be bounded. So this work was continued after Perrick in 1971. And finally, Sam Buss in 1986 introduced a hierarchy of theories, but starting with S12, which characterizes polynomial time. So the language here is a bit more sophisticated. You have plus times 0, 1, successor, a function known as smash, lengths, and division. And smash here is what allows you to introduce constants which may have a polynomial number of bits. So you can have long bit lengths. And I invite you to pause the video and read what the axioms for induction look like here. You have along side the basic axioms of arithmetic and how you would define smash. Sigma B1 induction, where now you are allowed a single existential quantifier that is bounded, and then an inner formula with either no quantifiers or extremely restricted quantifiers. And you might notice why this induction is stronger than normal induction, in that like the counter in this case is a polynomial number of bits, which each time loses 1 bit. So the induction process, you can imagine, happens in polynomial time, whereas simply in the normal case, you add 1 each time, and this might be exponential if your upper bound is n bits. So this is the intuition of why you might characterize polynomial time using this new form of induction. So just like in complexity theory, there's a whole zoo of theories. You have I delta naught, you have S12, you also have a theory like V0 introduced by Steve Cook. This characterizes logarithmic uniform AC0. You also have APC, which has a long history of study, but really first written down concretely by Yerzhebek, which characterizes some portion of ZPP. We even have questions of de-randomization, such as does APC, this probabilistic reasoning theory, equal S12, of which most of us believe to be no. So looking more at S12, S12 itself is actually quite powerful. And this is a very desirable property. We hope that these weaker theories can prove a lot. And S12 is able to prove the Cook-Levin theorem. It's able to prove the PCP theorem. It's able to prove the Schwartz-Ziepel lemma. This is a new result in STOC this year. And a major question on the metamathematics of complexity theory is, can S12 prove P not equal NP? Or can we maybe get an unprovability result? So let's talk more about provability of complexity type statements in bounded arithmetic, in particular in S12. So if L is some language decided by a Turing machine M of L, and suppose L is not decidable by a function in a complexity class C, and let's say S12 proves this. So S12 proves that L is not in C. Writing that down logically, then that means for every n, so every input length n, in every circuit C, there exists an x of length n such that the circuit C does not correctly decide or agree with M of L on x. Now, if you remember witnessing, a witnessing property for S12 says here that if S12 proves this statement, then there should be some polynomial time function which outputs this x here. And that polynomial time function R would be given n and C, and it would output this x. And this is just a refuter. So this links together this stronger notion of constructivity with that of CJSW of just there being a refuter for the lower bound. So we have a stronger notion here just giving a refuter. Okay, so can we duplicate the results of CJSW with bounded arithmetic? Can we say S12 proofs of non-constructive lower bounds imply breakthrough lower bounds? And can we show that some lower bounds are unprovable in S12? So for certain lower bounds, this is automatic, or right as we just saw, statements formalized as for all exists and then a formula. By witnessing for S12, we just extract a polytime refuter, and then we can apply the results of CJSW. But it turns out that many lower bounds cannot just be written as a for all exists sentence or schema of sentences. And a good example would be the existence of high KT strings. So how would you write it? You would write for every input length n, there exists a string of length n, where for every D here is going to be a pair of a program and an input to the program, your advice. So for every D, running the program, which is your Turing machine, on input, on some input, for time length 2b plus 1, this will not equal x. So this is saying that there exists a string x of k 2b plus 1. Of high K2B plus 1 complexity. Okay. So our witnessing property for S12 only applied to for all exists structured sentences. So if we have a sentence like that, that's for all exists for all, we would still hope to get some kind of witnessing. And it turns out we do. We just no longer get a normal polynomial time refuter. We now get a student-teacher refuter instead. So what is a student-teacher refuter, or in general, a student-teacher algorithm? You'll have a student, which is your normal, say, refuter. It gets as input 1 to the n, but now it has oracle access to a teacher, which can help with potentially very difficult, even NP hard queries. So let's run through an example with high KT. The student will take in 1 to the n, and it's trying to find a string x of high KT complexity. So it'll first start out running some computations just off of 1 to the n, and it'll eventually ask the teacher, does x work? And it might, in which case the teacher would say yes. But if not, the teacher gives back a witness that it does not. In this case, the witness is going to be a pair, a program and an input to it, which compresses the string X efficiently. So the student gets that response, and then we'll ask another question, and perhaps the answer is no, in which case we get another witness to the compression, until finally, after potentially many queries, the teacher will say yes. So there are some important properties of a student-teacher refuter in that, first off, the teacher is allowed to make any valid count, for example, at any step. So perhaps D prime is not the only compression scheme for X1. And the teacher is allowed to answer with anything that's valid. And we're also going to be looking at schemes which have only polynomially many rounds. So that's polynomial in n, where n is given in unary as input to the student. Okay, so what is this witnessing theorem then? So if phi is a formula of structure for all exists for all, then there's going to be a polynomial round student-teacher game, which outputs an x, witnessing this existential quantifier, satisfying phi. And in particular, for every teacher query, the teacher responds with a valid counterexample. Okay. So we're able to generalize CJSW from refuters to student-teacher refuters. So one of our main theorems is that there's no polynomial round student-teacher refuter against the always yes algorithm for deciding if a string X has high k to the n to the 2c plus 1 complexity, with the student running in time O of n to the c. So that's a mouthful. So let's go through step by step. So our student-teacher game has poly n rounds for any polynomial you desire. The always yes algorithm is going to be saying that every string has low k to the n to the 2c plus 1 complexity. We're just trying to find one that has high complexity. And the student here we're claiming has also restricted runtime itself. So in the original student-teacher game, we just said the student was in poly time, but here we're also saying the student can only run in time O of n to the c. Okay. The idea here really parallels the idea for the constructive proof in the deterministic time hierarchy theorem. So if a student S first queries the teacher X1, the teacher actually has a very simple response. It's just going to be the code of the student S, right? Because if S runs in time n to the c, then by definition, whatever it spits out, so X1 cannot have k n to the 2c plus 1 complexity or high complexity, since it has the code of the student compressing it. So we have an easy automatic response from the teacher, just the code of the student. And you can take this idea and run with it to compress the teacher away and just have a single student with no teacher necessary, which outputs this string. And it will do so in less than n to the 2c plus 1 time. And that will be a contradiction with the fact that this string is supposed to have high Kolmogorov complexity. Okay, so from this result, given that S12 has this witnessing, this KPT witnessing for all exists for all sentences, do we get unprovability in S12 as a corollary, right? Since if S12 proves there exists high KT strings, then we extract the student-teacher refuter, which we know shouldn't exist. So do we get unprovability as a corollary? And it turns out the answer is no, not at all. And the reason why is that when we apply KPT witnessing to high KT of B, where B is this, well, here it's C, this C parameter, the output might be a student that runs in time n to the 100B. We have no control over the runtime of the student when we apply witnessing. So in that sense, there's no contradiction because we require a very strict time bound on the student in our main result. So how could I go from this result to unprovability in S12? How do I enforce the student to have runtime n to the b? And the answer is to look at the uniformity of proofs. So in theory, stronger than S12, like this theory I briefly mentioned, APC corresponding to ZPP reasoning, you are able to show that these high KT strings exist. And in fact, it is the same proof for every C, C being the exponent in the time bound. If we insist that S12 proofs of this schema of formulas similarly must be uniform, then maybe we'll win. Because if it's the same exact proof, then hopefully we'll extract the same exact student-teacher game refuter. And then as long as we bring the schema parameter, C, larger and larger, and the student stays a fixed complexity, then eventually we will get a contradiction. Okay. So now I'm going to introduce some terminology to introduce a conjecture. Fix some universal function symbol, which run, which is just going to be running Turing machine M on input A for S many steps. And then after doing so, outputs the contents of the tape on M. Okay. So I'm going to have a schema of formulas, which we'll call a poly runtime schema. If it is a collection of formulas phi, and which has a free variable p, only occurring in terms of the form run of MAP. So p is a free variable specifying runtime of a fixed program. And the schema is just going to be varying this runtime. Otherwise, there are no modifications to the sentences in this schema. So pretty much anything you can think of has this structure, including high KT, as well as the deterministic time hierarchy theorem. So we would introduce, given these polynomial runtime schemas, a new kind of proof-theoretic conjecture on uniform proofs, witness hypothesis for uniform proofs, which we shorten to WUP. And what this says is that if S12 proves a poly runtime schema for almost every sentence in the schema, or even just infinitely many in the schema, then there is some fixed student-teacher game which correctly witnesses X in the existential quantifier. For infinitely many C, C the schema parameter. Assuming a WUP for S12 is true, then that means we do get unprovability. We get S12 does not prove high KT of C for infinitely many C. And another corollary we get is that assuming a WUP for S12, S12 does not equal APC. We finally separate these two theories. And this strengthens a recent result by Alongo, Lee, and Williams, who in 2023 showed that assuming two hypotheses, first that NP is not contained infinitely often in CoAM, and also the existence of indistinguishability obfuscation, then a slightly weaker theory, PV, does not equal APC. So we completely remove both the cryptographic assumption and the complexity assumption, instead just have this proof theoretic assumption on these witness hypotheses being true. So this second corollary is actually nice for two different reasons. First off, separating these bounded arithmetic theories is a lot like separating uniform circuit complexity classes. In that sense, it should be way easier to separate these bounded arithmetic theories than to prove that the strongest forms of cryptography exist, like indistinguishability obfuscation. As well, and this is a quote from Jan Pick, that we will not make progress in bounded arithmetic without introducing new logical tools. So the purpose of introducing these witness hypotheses is that we're introducing new logical tools and methods to get at the separations of these theories. rather than just using black box complexity theoretic assumptions. Okay, so given all of this and the amazing applications of witnessing hypotheses, why on earth should you even believe that they're true? And so it turns out there are many really good reasons. First off, a lot of the proofs we have in this other theory, PV, as well as S12, are examples of witnessing hypothesis behavior. So a perfect example is the deterministic time hierarchy theorem, where it is a fixed refuter, agnostic to this parameter B, for all these runtimes. It is the same refuter for all of them. Another good example would be the conversion of K-tape Turing machines into two-tape Turing machines. And this is also a fixed process, regardless of the number of tapes. And we list many other examples in our paper. Another reason is that these witnessing hypotheses share a lot of similarity to a very old and well-studied proof-theoretic conjecture known as Kreisel's conjecture. So when I write n underlined, that'll denote the successor of zero composed n times. So in logic, just n. And if piano arithmetic proves for every n, phi of n, in some k lines where k is an absolute constant, then that means there's actually just one proof which proves them all. So this Kreisel's conjecture is really a uniform proof conjecture that if I can prove this schema of phi, plugging in the schema parameter n, in a fixed number of lines, then I actually just have a single proof for all n phi of n, and I just have to prove that statement, and then I can substitute in whatever n bar I want. Okay. And an amazing thing about Kreisel's conjecture is that it's actually true for some axiomatizations of PA. It's also true for any finitely axiomatizable theory, of which bounded arithmetic theories are, or at least many of them. Now, whoops themselves are not exactly like Kreisel's conjecture, but you can strengthen whoops to get something that seems very similar. So I can strengthen the whoop to include a line count. So I also assume that S12, say, has a fixed line cap to prove each sentence in the schema. And then, say, you can get the conjectured witnessing. So one might ask, is there any hope in proving these witnessing hypotheses, either the more powerful one or the fixed line count one? And in general, we have no idea. But for a very strong whoop, so without this line count lower bound, or upper bound rather, it might actually be very hard. So in our paper, we introduced this theory V0 smash. And this theory characterizes polylog uniform, quasi-polynomial size, AC0 circuit reasoning. And it turns out that a witnessing hypothesis for this theory implies P not equal NP. So for some theories, it seems that a whoop is out of reach, and we have no hope of proving one. We have no such results for S12, for PV. It is solely for this theory, so it might be that there are actually no barriers if witnessing hypotheses turn out to be true. So I'll wrap up with some open questions for this work. First off, can you use witnessing hypotheses to get maybe conditional unprovability of the non-deterministic time hierarchy theorem from PV or S12? So right now, we have no idea what the provability of the non-deterministic time hierarchy theorem is. We simply know that a theory a bit more powerful than S12, known as T22, is able to prove it. But we have no evidence that it can't be done better. And it is really of great interest whether or not it can be proved in S12. We would love some conditional results of unprovability there. It would also be nice to know if there are interesting things that happen when whoops are false. So this would be something really weird, because this would mean that there's some schema that of a search problem that S12 is able to prove for every slice, but there is no fixed proof. And it is seemingly impossible to come up with any search problem, at least that I can think of, which follows this behavior. So just from that perspective, it's interesting, but are there any actual consequences if whoops are false? And finally, are there large families of poly runtime schemas where whoops are true? So maybe we can't get a general whoop, but maybe there's some subset of formulas where we can hope to prove whoops are true. And that very well might be enough to get unprovability of the high KT scheme, for example. Thanks for listening.